I'm a first-year PhD student. I'm working in physics applied to complex matter, and I'm a UGA PhD student. So I'm working on the impact of quantum effects on the dynamics of proteins. And today I will present the STEREO experiment, which is a particle physics experiment. And the goal of this experiment is to measure a neutrino spectrum coming from the ILL reactor core, but also to investigate the existence of a fourth neutrino. So this is what I will show you. So very quickly, I will present you what I'm going to talk about. So first I will present neutrinos, then globally the different anomalies that occurred during the last decades and that made scientists require a neutron oscillation model to explain what happened. And also now they had to investigate the existence of a new neutrino, which is called the sterile neutrino. And so I will give more of a theoretical framework for this so we can understand what is important. And then why and how was STEREO experiment conceived, how it detects neutrinos, and how it can be discriminated from all the background that is very important around STEREO. And then to finish with, what are the results that have already been acquired and the different analyses that have been carried out. So first I will start with the presentation of neutrinos. So neutrinos is an elementary particle which exists in the frame of the standard model. So the standard model is the framework for weak, strong, and electromagnetic interactions. And it's divided into two types of elementary particles. You have the fermions which generate matter, and the bosons which carry forces, so the weak, electromagnetic, and strong interactions. And among the fermions, you have the leptons, which are particles that only are sensitive to weak interaction. So you have the massive leptons, which are the electron, the muon, and the tau particles. And for each of those particles, you have a neutrino. So we call that the flavors. There is the electron flavor, muon flavor, and tau flavor. And the characteristics of those neutrino particles is that they have their own antiparticles, which are the antineutrinos. They have no charge, they have no mass in the frame of the standard model, and they have half spin. And what is interesting is that there are already hypotheses that can seriously be taken into account that go beyond the standard model, among which the fact that neutrinos could have masses being light particles, and for instance, that they could be their own antiparticle. And so I want to give a very short timeline of the different discoveries that happened that I'm interested in. So first, Pauli invented the neutrino, and at that time he called it the neutron. And indeed, it was to explain the fact that the beta decay had a continuous energy spectrum for which spin and energy conservation was not obeyed. And so he had to invent this particle with a little mass that could explain the beta decay correctly. And the neutrinos started to be detected quite early during the 60s. So first, the electronic neutrinos by Raines and Cowan with the same kind of detection that is used in STEREO. Also in the 60s, the detection of the muon neutrino, and not before the beginning of this century, the tau neutrino wasn't detected yet, and it was detected at the Fermilab at the beginning of the century. And in the meantime, some scientists started to suggest that neutrinos could oscillate. So what does this mean? It means that a neutrino could oscillate between flavors upon propagation. So it could go from electronic neutrino to muon neutrino to tau neutrino upon propagation, depending on the distance from the source. And the first oscillation experiments started at the ILL in the 80s, but we had to wait until the beginning of some anomalies to understand that there could really be neutron oscillations. So I will first be talking about the atmospheric neutrino anomaly. Indeed, cosmic rays react with the nuclei that are in the atmosphere, and they create muon and electron neutrinos. And it happened that when we detect those neutrinos 10 kilometers far from the source, the ratio between the expected and the detected fluxes deviates about 40% from predictions. So it's the SNO experiment that showed that. And this was difficult to explain because there was a disappearance of some flavored neutrinos. And this is also what happened with the solar neutrino anomaly. Indeed, in the sun, there are some fusion reactions that create electron neutrinos that come from the sun and 10 to the 1,003 kilometers far from the source. We also saw that there was up to 50% of the flux of electron neutrinos that just disappeared, and scientists couldn't explain why. And for that, there is a new model, which is the fact that neutrinos would have masses, and this is why they would oscillate between flavors over propagation. So here we talk about detectors that are at least 10 kilometers far from the source. And so to explain quite quickly what are the oscillations of neutrinos, indeed, this was already an established picture at the beginning of the century. There are some mass eigenstates, and the flavor eigenstates are quantum superpositions of those mass eigenstates. So this is what I tried to show with the drawing there. If you take a flavor eigenstate, which is a rho, then you can write it as a superposition of mass eigenstates with different weights according to each mass eigenstate. And so this is what I tried to show here with the drawing. And so what happens is that upon propagation, the quantum superposition of the mass eigenstates will change over distance, and this will imply a change of flavor over propagation, be it in vacuum or matter. And for the moment, physicists have access to the squared mass difference that's unable to couple the mass eigenstates and the flavor eigenstates with squared mass differences about the milli-electron volt, so it's very light, but they still don't have access to the total mass of the neutrinos. And so it's still difficult to give a very precise model because there are still some uncertainties. And the anomaly we are interested in happened in 2011, and we still don't have answers for this anomaly. What happened is that a lot of experiments that were done on short baseline experiments, which means detectors that are less than 100 meters from the source, showed that there was a deficit of anti-neutrinos compared to the new predictions that were made with the new knowledge that scientists had on the anti-neutrinos. And so we are interested then in the anti-neutrinos which are produced by nuclear reactors. So nuclear reactors, such as the one in ILL, are huge producers of those anti-neutrinos. So in ILL, it's mostly uranium-235. And what happens is that after fission, the products will decay and create anti-neutrinos of the electronic flavor. This is why I write here this electronic anti-neutrino. And for every fission event, there are around 6 anti-neutrinos that are emitted. So that's a lot. But the problem is that those anti-neutrinos have very little cross-sections of interaction. So they are very difficult to detect. And in short baseline detectors, which means the distance between the core and the detector below 100 meters, we could observe those oscillations. Indeed, what happens with what we call the reactor anomaly is that there is a 7% deficit between the experimental and the predicted flux. So there is a disappearance of electronic anti-neutrinos. And the possible explanation would be neutrinos oscillations, because this way it would mean that when there is disappearance of electronic neutrinos, there is appearance of another neutrino. This is what you can see here. When you have one of the neutrinos that disappears, then you have the other one that appears, and this oscillates with distance. But the problem is that the squared mass differences between electron and muon neutrinos and electron and tau neutrinos are nearly negligible at this distance. So it means that there should be another neutrino at stake, maybe more than one. But the model chosen by STEREO is that there are the 3 normal flavors of the standard model, plus one neutrino that hasn't been discovered yet. And this neutrino is special because first, it's very heavy because the squared mass difference would be about the electron volt, so 10 to the power 3 more heavy than the other particles. And also it would be a sterile particle, which means that it doesn't contribute to weak interaction. It would be only sensitive to gravity. And this is why it would be very difficult to detect. And what I show on the right is the reevaluation of the neutrino spectra. So after the reactor anomaly, the scientists tried to compute some allowed regions with two parameters, this squared mass and what we call the mixing angle. I will talk about those parameters later, which are the two parameters important for oscillations, and saying that in these allowed regions of parameters, one can observe neutrino oscillations. And so just to give a very short idea of what happens, here I just wrote how you can write a flavor eigenstates with the different mass eigenstates over time. So indeed, the mass eigenstates and the flavor eigenstates are coupled with what we call a PMNS matrix. And here it's just the evolution over time of the flavor eigenstates. And then if we just stay in the case of the oscillation between only two flavors, in our case, we are interested in the electron antineutrino produced by the source and the sterile neutrino, which would be the neutrino that oscillates with it. We can compute the survival probability of this antineutrino, which is the square of its the projection of the eigenstates towards itself. And what we can see is that this survival probability is oscillating. So here you can see that there is an oscillating term which changes with distance, with a period that we call L oscillation, and with an amplitude that depends on this angle that we call the mixing angle. So there are two different important parameters, the mixing angle that will parameterize the amplitude of the oscillations, and the period here that depends on the squared difference of mass. And so this is how we get this condition, which is very important. It's the condition to observe oscillations. And we can see that there are three important parameters: the distance from the source to the detector, the energy of the incoming neutrinos, and the squared mass difference between the two neutrinos. And this is how we can conceive such an experiment. So we are interested in the disappearance of the electronic antineutrino. This is what we want to observe. And before stereo, with the reactor anomaly, there were already some good fits for the existence of an antineutrino. So it means that there would be this squared mass difference of 2 electron volts squared, and this mixing angle of sin to the square of 2 theta equal to 0.1. And those two parameters, as I said, are the important parameters because the mixing angle gives the maximum probability of conversion. So how much the electronic antineutrino will exchange with the sterile neutrino. And the squared mass difference will control the frequency of oscillations. So then to design a stereo experiment, the scientists decided to have the distance from the reactor to the detector about 10 meters, because this is where the anomaly is observed. And also the length of the detector was chosen to be 2.2 meters. Why? Because the length of the detector should be around the period of oscillations if we want to see something. And if we say that the incoming energy of neutrinos is about 4 mega electrovolts, which is in the middle of the energy spectrum we can see, and that the squared mass difference is 2 electron volts to the square, which is the best fit of the reactor anomaly, then we get oscillations that are about 2.5 meter long. And this reactor, so it's chosen to be 2.2 meters long, and it's divided into 6 cells. So indeed, it gives us 6 different baselines to observe the distortion of the spectrum, to observe oscillations. So here I show you a stereo experiment. You can see that it's in between IN20 and D19, just under the water channel. So it's where it is situated in the hall of experiments. And here you can see that basically it's composed of 6 different detectors here, photomultipliers, I will show you later, and also different shielding methods. So what are the goals of STEREO? First, it's to measure with high precision the evolution of the energy spectrum at short distance, which means investigating the existence of a fourth neutrino. And second, we want to measure more precisely the energy spectrum for a uranium-enriched core, because it will give more information about the anomaly, and also because this way you can monitor the thermal power of your core and also its composition in terms of fuel. And so here you can see that the rate of neutrinos that are emitted per fiction is really enormous. It's 10 to the power 19. But the rates that are detected by STEREO is really low. It's about 400 neutrinos per day due to the very small cross-section of interaction. So this is why, in order to have good statistics, STEREO needed to acquire a lot of data. So this is an experiment that was settled in order to start acquiring data in 2016 and was dismantled last year. And so it worked for a few beam times periods with in total 200 days on, but also a lot of days off, which is important to get rid of the background. And there was some maintenance in between because there were leaks between the different cells of the detector. So first I will talk about how we can detect neutrons. So neutrinos can be detected by inverse beta decay, which is already the way Rains and Cohen detected the neutrino for the first time. So there is a nitrogen-rich scintillator medium, which is doped with gadolinium. And what happens is that the electronic antineutrino comes in, collides with a proton that composes the scintillator medium, and it gives rise to a positron and a neutron. And then what enables to say that there was an antineutrino is the signature of this inverse beta decay, which is the delay between the two events that happen. First, the positron will collide with annihilate very quickly with an electron. So this is a prompt event. It happens nearly at the moment of the collision, and it gives rise to two gamma rays that are very energetic. And then there is the recoil of this neutron here. So first it will thermalize and then collide either with a proton or with a gadolinium nucleus. And so the delay between the two events, one which is prompt and one which is delayed about 16 microseconds after, is the signature of such an event. So the inverse beta decay can be, so the inverse beta decay is, detected through this delay between events. And then the neutrino spectrum is inferred mostly from the positron kinetic energy, because this is the prompt event that is the most energetic, and because it gives right away the kinetic energy of the neutrino. And so how is composed STEREO? First, you have 6 target cells, which are the gadolinium doped scintillators. And those are the different cells where one can observe the inverse beta decay. And in between cells, there are highly reflective walls, because we don't want we don't want, for instance, to have a prompt event in one cell and the delayed event in the other one. So it's highly reflective to avoid crosstalk. And all around those target cells, there are gamma catchers. They have 2 roles. First, they actively detect all the background signals, so the neutrons and gamma rays coming from other instruments. But also they can also observe the different gamma rays that can escape from the target cells. Then the readout is done by 48 photomultipliers that are spread among the gamma catchers, target cells, and VTOs. And then there is also calibration. So there are internal tubes which contain different radioactive sources, which are gathered all around to be able to translate the charge that goes into photomultipliers into energy. So this calibrates the detector. And there are also calibration tubes outside. So what happens is that we have this input, the scintillator charge. Then we apply all the calibration that is done into the tubes, that is done also by Monte Carlo simulations. And this way we can reconstruct the energy of the incoming neutrinos within and between cells. And this enables to convert, scale the energy. And then what we really got at the end is the energy of the movement of the positron, the pulse shape of the prompt event, the energy of the neutron capture, which is the delayed event, and the time between the two events, the prompt and the delayed one. And then we apply cuts to the signal, because once we have the signal, how can we say that this is an inverse beta decay event? There are conditions of energy, because we know in which energy window the prompt and the delay events are supposed to occur. We have cuts on the delay because we know how quickly the neutron should be caught by the gadolinium nucleus. We have the cuts on the correlation distance between the prompt and the delayed event. And also we try to reject everything that can be correlated to another event that occurred just before. And so this is how you get the signature of an inverse beta decay, but the problem is that there is a lot of background, especially from muons that come from cosmic radiations. And there are two problems with the muons. There is the muon signal, but also the fast neutrons that are produced by the muons. And the problem with the fast neutrons is that their signature is very close to the signature that you would have with an electron anti-neutrino. So even during shutdowns, stereo works because you can subtract the off signal to the on signal. So first, there is a muon veto, which is what we can see here in blue. So it means that every time a muon comes, by Cherenkov effect, it will produce light because the muon will have a velocity that is higher than the celerity of the light in the medium concerned. And there also can be a veto in the detector when the fast neutrons produce proton recoil, and so it produces high energy signals. This is why also we add some cuts and rejections. Every time there is a muon coming in the veto, everything that happens below 100 microseconds after in the detector is rejected. And especially what is very important is that you can discriminate the pulse shape coming from fast neutrons from muons and coming from the electronic anti-neutrinos, because the pulse shape will be different. You will have different type of tails. And so calculating the charge of the tail over the charge of the tail and the total charge will enable you to discriminate proton recoils from fast neutrons from electronic recoils from electronic neutrinos. So what I was talking about here is how we get rid of the background, knowing that there are signals that can be very close to the signal of an anti-neutrino. There is also passive shielding, because this stereo experiment is in between two other experiments, which are D19 and IN20, and it produces a lot of neutron and gamma background. So there is passive shielding. Here you can see there is concrete, lead, polyethylene, and especially IN20 is producing high magnetic fields, and it can disrupt the functioning of the photomultipliers. So this is why they are recovered with new metal layers. And so all this passive shielding also enables to get rid of the background. And so now I will talk about the different results that were required. So there is a lot of work done on statistics, systematics effects, which are very difficult to explain. But already we can say that 65,000 neutrinos were detected during the elaboration of stereo. And the scientists got this anti-neutrino spectrum that is here normalized to predictions. And one can see that from 2 to, so the spectrum goes from 2 to 8 mega electron volts, and up to 6, the predictions are very close to the detected spectrum. But especially what we can see is that they also managed to calculate the observed VC's expected flux, so that it can also give information about the reactor anomaly. And for the moment, stereo has the most precise estimation among the different detectors that are close to enriched uranium cores. And so it means that stereo has very good precision, very good results. And what we are interested in is, are there oscillations between the electronic neutrino and the sterile neutrino? So they did a chi test on the null hypothesis, which says there are no oscillations. So we can write it in a more mathematical way. It means that we would not have a mixing angle. We would not have this squared mass difference. So the hypothesis we make is there are no oscillations. And the p-value according to this test is higher than 0.05, which means that we cannot reject this hypothesis. So what does this mean? This means that there might be no oscillations at all. So then the scientists derived the exclusion contour using Monte Carlo method on all those couples of parameters, the mixing angle and the squared mass difference. And what we can see is that in the allowed region here that was allowed by the reactor anomaly, so it was the region where we said there could be oscillations, most of the couples are already excluded by stereo data with a 90% confidence level. And those are the preliminary results, but afterwards, there were also even better results with a 95% confidence level. And what we can see that is even more obvious is that this time the star that you can see is the best fit according to stereo data. And even the best fit from stereo data is excluded by this Monte Carlo method. So indeed, stereo seems to give a lot of information about neutrino spectra, but not so much, about the oscillations for the moment. It seems that there might not be oscillations between the electronic anti-neutrino and the sterile neutrino. So what I want to say as a take-home message is that there were some anomalies that entailed scientists to draw a new model, which is oscillations between flavors of neutrinos. And in short baseline instruments as stereo, we should be able to observe this. But this detection requires to separate external events from neutrinos, and this is a lot of work. This is shielding, cut, statistical background subtraction, and also even with good statistics and corrections of systematic effects, it's very difficult to claim that we have a discovery in particle physics. So here is the bibliography. And I really want to thank Mr. Soldner, who really helped me a lot to understand what was at stake and what was important. And I also want to thank Alice for the support, sharing tips, and talking about the PhD seminar.